This week in the lab we're going to be learning about the operation of amplification, and we'll be looking at some semiconductor devices known as operational amplifiers that make it very easy for us to construct circuits that will provide amplification of different sorts. By amplification we mean taking a voltage or current, but in general taking a signal that is smaller and making it larger or amplifying it. You'll notice the blue signal is oscillating here at a given frequency, and it oscillates between plus and minus 1 volts. The green signal is the exact same signal as the blue one. It has the same frequency, it would have the same phase, but you'll notice the green one, instead of going from plus or minus 1 volts, it goes from plus or minus 5 volts. So if the blue signal, if we were to call that V1 of t, and it was equal to 1 times the cosine of omega t, and the green one we called V2 of t, it would equal 5 times V1 of t, or in this case 5 cosine of omega t. So the idea with amplification is whatever the original signal is, the amplified version will be exactly the same, only have a different amplitude. And you can actually do amplification that increases the amplitude, and you can do attenuation, which is a shrinking of the signal. The amplifiers we're going to be using are a little silicon amplifier that comes in what's known as a dual inline package or a DIP package. Dual inline means that it's got 2 rows of connecting pins. And when we're looking at a package like this, in general a semiconductor device like a semiconductor package like this, there's always a top. And the top is marked either with a dot here or a notch in it. Other times there'll be a dot there, and sometimes you'll have both. However they denote it, there will be a top to the package. And then the pins are numbered starting at the top left hand right here, starting with pin 1 and then going on down. In this case it's a 14 pin chip, so you've got 7 pins, pins 1 through 7 on this side, and then you come on over and pins 8 through 14 on this side. They're made to go into a proto board so that the pins on one side sit on one side of the gap, and the pins on the other side sit on the other side of the gap, with each pin lining up with a row of dots, or with a row of holes. So you can make connections to pin 1 in any one of the dots left showing here, and you can make connections similarly on the other side to pin 14. And of course, because of the gap here, pins 1 and pin 14 are not connected to each other. Now inside this package that we're looking at, the LM324, there are actually 4 independent operational amplifiers. The symbol for the operational amplifier is a triangle, and they have 2 inputs. One's denoted with a minus sign, one's denoted with a positive sign, and there's an output. The term operational amplifier has a little bit of a legacy. These amplifiers were originally used in what were known as analog computers, electronic devices that could perform mathematical operations on analog signals. We've already seen that amplifiers can scale or either amplify or attenuate a signal, but they can also perform other mathematical operations. You can add signals together using the different inputs. You can subtract one signal from another signal. You can integrate or differentiate. Those are 2 functions or mathematical operations coming from calculus. But you get at the idea is that these operational amplifiers are designed to perform mathematical operations on the amplifier, or on signals. So this package has 4 amplifiers. You'll notice that each one of them is independent. Each one of them has an output and 2 inputs. And you'll notice in the packaging that the output terminal is brought to the corner pins of the amplifier. So there's a nice symmetry to help just keep things straight. The corner pins are the outputs, and the next 2 pins away from the output pins are the input pins. Now, just a little bit of background on the symbols marking the inputs. One's marked with a negative sign, one's marked with a positive sign. That does not mean that you can only hook negative voltages up here or positive voltage up here. In fact, you can put either positive or negative voltages here. You can put either positive or negative voltages here. What they're meant to indicate is that, and we'll note that the terminal marked with a negative sign is known as the inverting terminal, and the terminal marked with a positive sign is known as the non-inverting terminal. And by inverting or non-inverting, what we mean is that any voltage that is connected to the inverting terminal will manifest itself at the output with a change of sign. In other words, the impact or the influence of the output by voltages connected to the inverting terminal will be opposite in sign. So if you put a positive voltage on the inverting terminal, it will manifest itself where its impact at the output will have a negative sign on it. If it's positive here, it shows up here negative. If it's negative here, if it's a negative voltage here, you'll see a positive voltage here due to that voltage. In other words, this output will have the opposite sign as the voltage here, as the voltage connected to the inverting terminal. On the other hand, voltages that are connected to the non-inverting terminal will not have a reversal of sign or an inversion of sign. That means that a positive voltage here will be seen as a positive voltage at the output. A negative voltage here will be seen as a negative voltage at the output. Because this is an operational amplifier, then we will see the sum of these voltages, the difference of these voltages, scaled values of those voltages. And that's what we're going to be learning about this week in lab. Here's a typical op-amp configuration where we've got the operational amplifier with its input, the inverting terminal, the non-inverting terminal, and we have two different voltages. V1 is connected to the inverting terminal through R1. V2 is connected to the non-inverting terminal at just connected directly to it. So the effect here at the output for V2 will have the same sign as V2. When it's positive, it'll be positive here. When it's negative, it'll be negative here. On the other hand, V1, because it's connected to the inverting terminal, its effect will be opposite in sign. Now, when we connect, and is frequently done in an operational amplifier circuit, there will be some sort of a connection going from the output to the inverting terminal. This is what is referred to as negative feedback. It's beyond the scope of this class, and so we don't want to dig deeply into it, but suffice it to say that negative feedback will be necessary to keep the amplifier stable. Now, there are some situations where we won't want that, where we won't have feedback, but in general, a negative feedback resistance or a negative feedback path is necessary to stabilize the amplifier. Or by stabilize, we mean to constrain the output. When modeling the amplifier, we realize then that this output can be thought of as a multiplied or a scaled version of whatever the voltage is on the non-inverting terminal minus the voltage on the inverting terminal. Or the output is going to be some large value A times that difference. Now, we'll talk more about it in class, but there are some general approximations that we need to understand in using these amplifiers. The first approximation is that the currents going into the inputs are very, very small. In fact, they're on the order of microamps, or 10 to the minus 6th amps. So in our analysis, the currents going into the non-inverting and the inverting terminal are going to be thought of as being zero. We'll approximate it as being zero. We're going to neglect those currents. The next approximation is that the voltage between these two terminals is going to be very, very small. Not zero, not exactly zero, but very, very small.
In our analysis of it, we're going to assume that it's very, very small. In fact, the next approximation is that they are equal to each other. Now, here's where it starts to get just a little bit confusing. This gain term in an ideal op-amp is huge, frequently on the order of 10 to the 5th, 100,000. So it's going to take whatever this difference is here, which is relatively small, and multiply it by a very big number, so that the output then is a very large number times a very small difference to give us some reasonable number. We'll talk about what reasonable means here in just a second. The other approximations are that the output resistance is very small, which means that over a wide range of currents, over a large range of current, the output is going to remain constant. In other words, for a reasonable amount of current out, the voltage at the output will not be affected by the current out. And the other, this is just a kind of a natural consequence of our first approximation that currents are going in. We assume then that the input resistance is very, very large, approaching infinity, which means that there's no current going in there. Now, what do we mean that we have a reasonable output? Well, these amplifiers have to be powered by a power supply. They could be batteries. They'll be DC power supplies. They could be batteries. They could be our power supply, just a standard DC power supply. But let's just say, for example, this was connected to a minus 12 volts, and this was connected to a plus 12 volts. That's like when you plug your iPod into your docking station and amplify the music. You have to plug the docking station into the wall to serve as a power source. The power to make this bigger signal comes from your power supplies. Now, it only makes sense that you're not going to be able to get a larger voltage out than what your power supplies are. You can't reach anything greater than 12 volts on the positive side. You can't reach anything less than negative 12 volts on the negative side. So for this output to be reasonable, it needs to be between negative 12 volts and positive 12 volts. And it's that feedback resistor. Whoops, I'm taking it the wrong direction. This is upside down from the ones we've been looking at. There needs to be a feedback resistor going from the output to the inverting terminal to constrain the output between those two voltages. Because those become the limits, those are sometimes referred to as the rail voltages. They are the voltages beyond which the output will not go. So in the lab for this week, we're going to be connecting a number of different amplifier configurations, which means we're going to be putting different kinds of signals into the inverting and the non-inverting. We're going to learn how we can control the actual gain or the amount of amplification that we're going to see at the output by carefully selecting the values of these resistors. We'll talk more about those in lab, but that should give you a good overview of what we're going to be talking about, and we'll see you in class.